My screen is visible, right?
Yes, sir.
Good evening. My name is Renuraman Sahu, and today we will be discussing some of the questions of assignment 2 of this year and the previous year, and we will see some techniques how to solve the problems. Uh, so the first question is, what is the probability of occupancy of a state of energy which is 0.05 electron volt above the Fermi energy? So it has given the Fermi energy, and what we want to find is uh, the probability of occupancy of a state. So the probability of occupancy is given by f of E, which is 1 by e to the power e minus ef. Ef is the Fermi energy over kBt plus 1. Okay, it has given the energy. The energy is 0.05 electron volt above the Fermi energy, which is EF plus 0.05 electron volt. Uh, and we are told that the temperature is 300 Kelvin, and the Boltzmann constant is given. So from here we will get E minus EF is equal to 0.05 electron volt, and for kBt, what do we do is kBt is equal to so since it is already in electron volt, so we will use this value 8.625 into 10 to the power minus 5 electron volt per Kelvin, and the temperature is 300 Kelvin. So this will give me 0.026 electron volt. So this is for 300 Kelvin, it is always 26 milli electron volt or 0.026 electron volt. This is a very standard value, like you should like remember it. So we're discussing about the probability of occupancy of a state. The energy is given, so energy is this, and so we got E minus EF equal to 0.05 electron volt, and the thermal energy at 300 Kelvin, it is 0.026 electron volt. Now we just have to put in this formula 1 over e to the power 0.05 divided by 0.026 plus 1. This is nothing but so you just solve it and you will get 0.1 to somewhere around this. So this is how you solve this question. Now we go to the next question. So it is asking, continuing with the previous problem, okay. So the next question is, it is related to the previous problem. So what is the probability of occupancy of a state which is 0.05 electron volt below the Fermi energy? So here what I want to highlight is, say there are two techniques. Either you can use the formula f of E is equal to 1 over a to the power e minus ef over kBt plus 1. So now since it is asking below, so E is equal to EF minus 0.05 electron volt. But since you have calculated what is the occupancy for uh, what is the occupancy of the level which is 0.05 electron volt above the Fermi energy, now you don't have to do anything. So it is there is a very simple way. So at zero temperature the Fermi function looks like this, f of E and A, and this is at EF. So you have calculated what is the value of the Fermi energy at 0.05. This value is EF plus 0.05 electron volt, and now you want to find what is the value here. This you have already found in the previous question, EF minus 0.05 electron volt. The Fermi function, it is such that if you see the plot of the Fermi function, at some finite temperature it is like this. So and at AF it is always 0.5. 0.5, here it is 1 and it is 0. So there is a symmetry here, like the so this is this distance, so from here to here and here to here, if you break it down, so this interval is same as this. So basically if this value is delta EF, what you have is f of EF, EF is the Fermi energy, plus delta E plus f of EF minus delta E is equal to 1. Now in the previous question, what you have found in the previous question, this is the value you found for energy which is 0.05 electron volt above the Fermi level. So you found it here, somewhere here. Okay. So now what you can do is, since you know this value, so you know this value. This value is how much? This value from the previous question, it is 0.127. 0.127 is this height. So to calculate this, you just have to do 1 minus 0.027. Okay, so this is one way, and so this will give you this will give you 0.0.127, or it is like 1 minus 0.13, so 0.87. So this is how you can solve these problems. Now we come to the third question. At what temperature would the characteristic thermal energy kBT, kB is the Boltzmann constant, what is the temperature at which the thermal energy is equal to the Fermi energy? So this is the thermal energy. We have to find the temperature. This has to be equal to the Fermi energy. It is asking the temperature at which this condition is satisfied. So here everything is given. You just have to find the temperature. EF is equal to 11.2 into 10. So basically T will be EF over kB. 10 to the power minus 19 joule, and kB, it is given, kB is 1.38 into 10 to the power minus 23 joule per Kelvin. So this will give me 8.116 into 10 to the power minus 10 to the power 4 Kelvin. So your answer will be this. Now the fourth question, here it has given the relaxation time for free electrons of the copper. So we have to find this, find the relaxation time of the free electron in copper if the density of the mobile electrons, so density of the mobile electron is given, it is 8.4 into 10 to the power 28 per per meter cube. The resistivity is given. The resistivity is related to conductivity as 1 over sigma. Sigma is the conductivity. So the resistivity at room temperature is given as 1.7 into 10 to the power minus 8 ohm meter, and mass of the electron, it is 9.1 into 10 to the power minus 31 kg. Okay, and the charge of the electron is given 1.6 into 10 to the power minus 19 coulomb. So now what we have to do, we have to find the relaxation time tau. So we have the formula sigma from Drude theory, sigma equal to n e square tau over m. So we have to find tau, and conductivity we know because we know the resistivity. So it is 1 over rho n e square into m. So you just put everything together. So 9.1 into 10 to the power minus 31. Rho is 1.7 into 10 to the power minus 8. N is 8.4 into 10 to the power 28, and is 0.6 into 10 to the power minus 19 whole square. So this will give 2.49 into 10 to the power minus 14 seconds. So since all this, so whatever I am putting in this formula in SI unit, this will also be in SI unit. So this is your relaxation time. Now it is asking about, so the next question, it is asking about the volume of the Brillouin zone of sodium, and it has so volume of the Brillouin zone of a sodium, and it has given that the unit cell is it has an edge of 4.23 angstrom, and the primitive cell is cubic with BCC structure. So the BCC structure is, so BCC structure is nothing, it is a body centered cubic. What it means is it will have atoms in the corner, in all these corners, and one in the body center, in the center of this body. So the number of atoms in a primitive cell which is in this case is BCC, it is 2. Why? Because 1 is so the number of atoms, so 1 is this body centered one, and there are 8 atoms in the corner, and each of them is contributing a volume of 1 by 8. So why 1 by 8? Because this one atom is shared by 8 such cubes. So it is 8 into 1 by 8, which is 2. So number of atoms in a primitive cell, it is 2. So for a unit cell, so the volume of this, so these 2 atoms are in a volume of is equal to a cube. Now volume occupied by 1 atom. So that is basically your unit cell. So the volume of unit cell is volume occupied by 1 atom. Volume of unit cell. So it is a cube by 2. Now the volume of Brillouin zone is given by, it is 2 pi whole cube over V, where V is the volume of 1 unit cell. So it is 2 pi whole cube over a cube in by 2, which will give me 2 2 pi whole cube, and you have to put this value 4.23 into 10 to the power minus 10, because 1 angstrom is, so this is 4.23 into 10 to the power minus 10 meter whole cube. If you solve this, you will get 6.55 into 10 to the power 30 per meter cube. So this is how you solve this question. Now we go to the next question. This is on Hall effect. A Hall probe consists of a copper strip with electron density. Electron density is given as 8.5 into 10 to the power 28 electrons per cubic meter, and it is 2 centimeter wide and 0.1 centimeter thick. So to get a better visualization, let us draw this. So n is given, it is 2 centimeter wide and 0.1 centimeter thick. So this is 2 centimeter and this is 0.1 centimeter. The magnetic field, so it is asking what is the magnetic field. So magnetic field V is applied, and the Hall potential they are able to measure is, so let's say this is VH, Hall potential, this is 4 microvolt, and the current passing through it is 50 ampere. I is equal to 50 ampere. So the way we solve this is, so basically, if in case you have forgotten the formula, what you do, you think of a charged particle in this volume, and it is derived by balancing the force on this electron due to the Hall field and the magnetic and the Lorentz force due to this magnetic field. So the Lorentz force on the electron due to the magnetic field is given by E into V into B. This V is the drift velocity of this electron, and the Hall field. So because of this magnetic, because of this force, the Lorentz force, this charge will get separated. So here the electrons and protons will get separated, and there will be a Hall field developed, and in that Hall field will oppose that charge separation. So and at equilibrium it will balance that, the force due to that Hall field will be E into EH, and it will balance the Lorentz force. So this EH is given by, EH is related to the Hall voltage as EH equal to VH over this distance. Let's say this distance is D. VH over D. So this the drift velocity into the magnetic field is equal to, so this electron cancels, so E cancels, so it is EH, and EH is VH over T. Now we know that the current density is nothing but NE into V. This V is the drift velocity. So velocity we can get it from here. It would be J over NE, and J is the current density, so it will be I over A and times E. So you just put it here. So J over NE into B is equal to VH over D. We want to find the magnetic field. So what we do is we keep the magnetic field on one side and we take everything the other side. J into NE, and J we will write it as I over A. A is the area of this cross section, this area. So VH and E over T I over A. So we just now have to put all the values. So VH is equal to 4 into 10 microvolt means 10 to the power minus 6. N is 8.5 into 10 to the power 28. E is 1.6 into 10 to the power minus 19 electron. A is the area of the cross section. The cross section area A will be given by 2 centimeter into 0.1 centimeter. So let me just write A is equal to 0.1 centimeter means 10 to the power minus 2 meter into 2 into 10 to the power minus 2 meter. So it is 0.2 into 10 to the power minus 4 meter. So into 0.2 into 10 to the power minus 4 meter divided by D. So this D is what? It is the distance between this two. So this is 2 cm. So 2 into 10 to the power minus 2 into current. The current is given as 50 ampere. So 50 ampere. So when you put all this, you will get the magnetic field. So the magnetic field will be so when you solve this, it will be around 1.1 Tesla. Okay. 1.1. So this is how you solve this question. Now we go to the next question. So it is asking the dimensional formula of the Hall coefficient. The Hall coefficient RH, it is given by 1 over n E, where n is the number density, and E is the charge. And charge has a unit of coulomb. So what you can do is, so A is here, A is what? A is ampere, which is the unit of current. T is the unit of time. So the number density, it has a unit of per meter cube, which is nothing but L. Meter is the unit of length. So the dimension of n will be so the dimensions of this n is L minus 3. So for the charge, what we can do is we can just write it as, so we want to find the dimensions. The dimension of RH, so by this square bracket I mean the dimension, it will be same as the dimension of n, and here we have the dimension of electron. So the dimension of electron will be n. So what we will do is we will divide it by time, because charge by time will give me current, and will multiply the dimension of time. So this is 1 over, so n will have a dimension of per meter cube. So this will have a dimension of ampere, and this will have a dimension of T will have a dimension of time. So RH will have a dimension of L3 A minus 1 T minus 1, and M has to be 0. So it will be M3 M0 L cube A minus 1 T minus 1. So this is going to be their answer. Now let us go to the 8th question. So what it has given is, let us consider a silver ribbon whose cross section is, it has already given a cross section. So let us just draw so that we can visualize it better. So the cross section is 1 cm, is 1 centimeter and this is 0.2 centimeter. This ribbon carries a current of 100 ampere along its length, and it lies perpendicular to the magnetic field of magnitude 1.5 Tesla. So let us say that the magnetic field is along this direction, and the magnetic field has a value of 1.5 Tesla. The density of electrons is given, n is equal to 5.9 into 10 to the power 28 electrons per cubic meter. So we have to find the Hall potential between the edges of the ribbon in microvolt. So what is this Hall potential? Hall potential, again, as we discussed before. So there is a voltmeter, if it is attached like this, transverse to this direction of current and perpendicular to the magnetic field. So the voltage which we measure here will be your this will be your Hall voltage. So again we will use the same technique of balancing the Lorentz force and the Hall force due to the Hall field. So EVB is equal to E times the Hall field. So E cancels E, V is, since J equals NEV, and we have V equals J over NE. So J by NE into B is equal to EH. So what is EH? EH in terms of so E is the Hall field and it is related to the Hall voltage by, so let us say that this distance is again D. So it is VH over D. We want to find this Hall voltage. So VH will be J over NE into B into D. So J is nothing but current density. So current density is I over A into 1 by NE B into D. Okay, now see A can be written as so this distance is D is 1 centimeter and this height is 0.2. So let me say this is height. So I times, so area of cross section A will be H times D. So H D 1 over NE B into D. So this D will cancel this D and I have I B over H and E. So I is given as 100 ampere, B is given as 1.5 Tesla, height is 0.2 centimeter. So this is height. So height you can 0.2 into 10 to the power minus 2 meter, and N you have been given, N is given, and electronic charge you know. So basically VH will be equal to IB over H and E. We just put all the values, 100 into 1.5 divided by H 0.2 into 10 to the power minus 2, N is 5.9 into 10 to the power 28, and E is 1.6 into 10 to the power minus 19 coulomb. And so this will give me VH is equal to 7.9 into 10 to the power minus 6. So since all the units we have put here are in SI unit, here also we will get in SI unit. But 10 to the power minus 6, so this you can write as 7.9 into 10 to the power minus 6 volt. So 10 to the power minus 6 volt is your 1 microvolt. So 7.9 microvolt. So here N will be equal to 7.9. So here this N is not the, this N is some number. This is not the same as this N. This N is your number density of electron. Okay. So this is how you solve this question. Now let's go to the next question. Uh, in a Hall experiment or on an intrinsic semiconductor. So it is given intrinsic semiconductor, which of the following statements is or are correct. So what do we mean by intrinsic semiconductor? So the number density of the positive charge carriers, which are the holes, the number density of holes is will be same as number density of electrons. Okay. Uh, so since these number densities are same, so one might think that okay, let us just draw Hall voltage again, the setup for the Hall voltage again. So and some current is going I. So let us say that this electron is there is this electron and the magnetic field is from like this, or which is magnetic field is going into the page. Since current is this direction, in positive x direction, electron will go in this direction. Now we see the force on this electron will be by using, so F is equal to minus E V cross B. So if you do this, so V cross minus E V cross B will it will point along this direction. So this is force due to the magnetic field, FL, or the Lorentz force. So here all the electrons will be there after because of this presence of magnetic field, and the positive charge will develop here, and this will create the Hall field. Now in this, since it is an intrinsic semiconductor, it is so there will be same number of electron as the number of holes. So one might think that the Hall voltage is 0, but so one thing to note here is that another important factor comes into play, which is the mobility of carriers. And this mobility depends on the mass of the effective mass of the carriers. Effective mass. So usually the holes are heavier than the electrons. So the mobility of the electrons are more than that of holes. So electron can the contribution of electrons actually dominates the contribution of holes in this thing. So that is why the Hall voltage is not 0. Like if their mobility had been the same, or the effective mass had been the same of the holes, both the charge carriers, then it would have been 0. But so this will not be correct. So the Hall voltage is so this option is out of so this is wrong. Hall voltage is negative if effective mass of holes is larger than those of the electrons. So this statement is true, that the effective mass of holes is larger than those of the electrons, but so you cannot just say that the Hall voltage is negative. So so voltage being positive or negative, one thing is that it is dependent on the convention on how you attach the how you make these contacts. So that is how you will get this one. So this you can this you cannot like say that it is the answer. So this statement is for sure it is correct. The Hall voltage depends on the mobility of the carriers. So this is correct. And the third statement, Hall coefficient can be used to estimate the carrier concentration in the semiconductor. So the Hall coefficient RH, it is a function of the number density of the electrons and the mobility of the electrons, and the number density, let's say number density of holes I am denoting as T. It depends on the number density of holes and the mobility of holes. Okay. So it can tell you what is the majority charge carrier in the semiconductor, but it cannot give you it will not give you an exact estimate of the carrier concentration in the semiconductor. Okay. So the correct answer is this. The Hall voltage depends on mobility of the carriers. So now we come to the 10th question. The Fermi energy of a metal is given. Fermi energy of a metal is EF equal to 5.51 electron volt. The average energy of the electrons at 0 Kelvin is given by E. So it is the average energy. So what average energy means? It is the average over all the electrons. So for that means what is the total energy of all the electrons divided by what is the total number of electrons. Okay. At 0 Kelvin it is given by this. Okay, average energy. The temperature at which the classical free particle will have this is given by will have this average energy is given by T. Then we have to find first what is the average energy and what is the temperature. Okay, so let us first find the average energy. So the average energy will be given by total energy. So average energy at 0 Kelvin. Okay, it is total energy at 0 Kelvin divided by total number of electrons at 0 Kelvin. The total energy at 0 Kelvin will be given by, so we will use the formalism of this density of states. So at 0 to infinity, the energy E of each electron. So first we'll see how many number of electrons are there. So G of E is the density of states. This is the number of states available per unit volume from energy E to E plus dE. Now GE/dE, so this will give you the number of energy levels per unit volume between E to E plus dE. Now we want to find what is the number of electrons. So that is why we have to multiply the occupation probability. So F of E, G of E, F of E into dE. This tells us what is the number of electrons having energy E to E plus dE. So this is the number of electrons. So now this many number of electrons will have energy. So we want to find what is the total energy, right? So now if you want to ask what is the energy, total energy of the system in the energy interval E to E plus dE, it will be given by E times G of E into F of E into dE. Now by using the same arguments we can say that the total number of electrons will be 0 to infinity G of E F of E dE. Now what we can do is so it is given that we have to find it at 0 Kelvin. So at 0 Kelvin the occupation probability, which is just the Fermi function, it is given by this step function EF. So F of E, and this is 1 and this is 0. So at t equal to 0, F of E will be given by 1 if energy is less than EF and 0 if energy is more than EF. So what we can do is, so we have this integration from 0 to infinity. So what we can do is we can break this integration 0 to EF E G E F E dE plus EF to infinity E G E F E dE divided by, similarly this integral also we can break it into two integrals, 0 to EF G E F E dE plus EF to infinity G E F E dE. Now what we can do, now we can use this formula. So f of e in this range is 1, so this is nothing but 1, this is also 1, but from ef to infinity this is 0. Ef to infinity f of e is 0. So here we are at this point of time we are imposing uh, at t equal to 0 what will happen. So since it is 0, so 0 times anything, so this we can neglect, and this we can, so this goes to 0 and this goes to 0. So what we have is just, so what we have is so now what we have is 0 to ef e g e, f of e is 1, so we don't have to write that, divided by 0 to ef g e d e. So if you go to the next page, so we have the average energy E is equal to 0 to EF E G E D E and 0 to EF G E D E. So now the density of states GE, it is given by 1 by 2 pi square 2m over h bar square 3 over 2 into square root of E. Okay, so all these are constants, so we can simply write, and the constants in the numerator and denominator, they will cancel out. So basically if we just write that 1 over 2 pi square 2m over h bar square 3 over 2 0 to EF divided by 2 pi square 2m square 3 by 2 0 to EF and square root E dE. So this constants cancel out and we are left with 0 to EF, this is epsilon to the power 3 by 2 dE over 0 to EF 1 by 2 dE. So if you just do this, you'll get EF to the power 5 by 2 divided by 5 by 2. So EF 3 by 2 over 3 by 2. And if you simplify this, what you are getting is 3 by 5 EF. So the average energy E is given by 3 by 5 EF. Right. Now you are given EF in the previous slide. EF is 5.51 electron volt. Okay, and you have to find E. So EF, if you put 3 by 5 into 5.51 electron volt, so it is 3 into 1.2 electron volt 3.3, so it is around 3.3 electron volt. So you already have so this option is your correct option. So now let us find if we are getting the temperature as this or not. So the temperature will be given by, so what it is asking, what is this temperature? The temperature at which a classical free particle will have the energy E. So the energy of a classical free particle is given by 3 by 2 kBT, energy of a classical free particle. So this, it is asking at what temperature the energy of that classical free particle will be equal to energy of this classical free particle will be equal to E. So now we already have this value of E. So what we'll do is 3 by 2 kBT is equal to E. it is asking for the temperature. So 2 by 3 into E over Kb. So now you just put everything. So it is 2 by 3. So this we have to convert to joule. To convert this to joule, what we can do is, so since it is an electron volt, we just have to 3.3 into 10 to the power 1.6 into so 1.6 into 10 to the power minus 19 joule. So you can write this as, this energy will be given by 3.3 into 1.6 into 10 to the power minus 19 divided by kb. Kb you have to write in joule per Kelvin unit. So this is in joule. So 1.38 into 10 to the power minus 23 joule per Kelvin. So you will get whatever the temperature in Kelvin. So and that temperature comes out to be so around 2.55 into 10 to the power 4 Kelvin. So which is your this answer. So this is how you solve this type of problems. Now let us go to the previous year questions, some of the previous year questions. Here you are given the Fermi energy of copper. So this is EF, you have already been given. The ratio of corresponding electron velocity. The corresponding electron velocity, how do you find? So you have to equate this with the kinetic energy, half mvf square. So the corresponding electron velocity is Vf, or the Fermi velocity. So it will be given by 2Ef over m square root. And now we have to take its ratio with the speed of light. So you have to find Vf over c, and you know all these values. So m is equal to 9.1 into 10 to the power minus 31 kg. Ef is already given in joule, which is SI unit. So you just have to put the formula and get the answer. So it is 2 into 11.2 into 10 to the power minus 19 over 9.1 into 10 to the power minus 31 kg and divided by 3 into 10 to the power 8. C is the speed of light. It is 3 into 10 to the power 8 meter per second. So if you calculate this, you will get 5.3 into 10 to the power minus 3. So this is the ratio. Now we go to the next question. Yeah. So now it is asking, consider n electrons in a volume V. So n electrons in volume V, and its energy is given as E is equal to 2 times, this 2 corresponds to the spin, sum over k less than equal to kf h bar square k square over 2m, the energy per electron and the pressure exerted by it. So energy per electron, so we have to so what it is doing is, it is summing over all the wave vectors which is less than kf, which is the Fermi wave vector. So this integral, it can be converted to so this summation can be converted to integrals, and when you go through that procedure, what you will, so this expression is nothing but, so energy is equal to, so energy per electron, let us see, understand this quantity. Energy per electron is, so this is the total energy. This total energy you have to divide by what is the total number of electrons. So this we have already found it, so it is just posed in a different way. So the energy per electron epsilon is given by the total energy E, so this energy over total number of electrons. Now it is just this is just a different way of writing the same thing. So how do we write this? Uh, it is sum over all the energy. So h bar square h square k square over 2m. You see that it is nothing but energy. So this thing is same as this the density of states into f of E dE into E. So if you want to know this exact derivation how it happened, you can refer to this as well. And this is at t equal to 0 because it is summing over all the energies which is less than the Fermi wave vector. Okay. So these two quantities are the same thing. And just now we have so the total energy will be given by the same technique, G E F E D E, and here we have to do 0 to E F, and this we have to do 0 to E F G E F E D E. Okay, so we have done just a few slides before here. That the energy, so this average energy E, this is nothing but E over N. Okay, this is what we have started with, E over N. Okay, and we got this formula, so we just have to put directly E over N is equal to 3 by 5 EF. Now from this we have to now we have to see what is the pressure. So let us calculate the pressure. So we already have this. Since we have this, we know the answer. But let us see how do we calculate the pressure. So we have the energy E is equal to 2 for spin K less than Kf h bar square K square by 2m. So if you do this, this is nothing but the expression of the Fermi energy. Uh, so since it is summing over all the vectors till Kf, it is nothing but A is equal to 0 to EF 1 by two. Yeah, so here E is nothing but your Fermi energy. And your Fermi energy is given by E F is equal to h bar square over 2m 3 pi square times the number density n by v into 2 to the power 2 by 3. So this is your total energy E. Okay, so the energy E is h bar square over 2m 3 pi square n 2 by 3 over v 2 by 3. So we want to find the pressure. Okay, to find the pressure, so we have to look into a thermodynamics equation. So in thermodynamics, so the change in the internal energy of a system is given by uh, it is given by T ds, where S is the entropy, means P dV. Okay, so if we want to calculate the S is the entropy, so we are not much interested in this term. Uh, so we want to find what is P. So the P will be P is given as P is equal to minus derivative of E with respect to uh, the volume V by keeping all other parameters constant. Okay, uh, so we just have to do partial derivative of E with respect to V, keeping all the parameters constant. So we already have E as this. So variable is constant. So pressure is given by minus dou E over dou V. So n will be constant and all other quantities, relevant quantities, will be constant. So now we just have to do this. So on doing this derivative, what we get is n 2 by 3. So it is minus 2 by 3 V to the power minus 5 by 3. So this you can write as h bar square over 2m 3 pi square n by v to the power 2 by 3, and so there is this minus sign, this minus will cancel this minus, so 2 by 3, and we have taken v to the power 2 by 3 into this, so it will be just 1 by v. So you see carefully, this is the expression for the energy E. Okay, this is same as this expression, so it is 2 by 3 E over V. So this is equal to your pressure. Okay. So your pressure is given by 2 by 3 into E by V. So that is what you see here. That is what you see here. Now the next question, it is related to the same formula. So what are the two important formula we have got is, one important formula is the average energy, the energy per electron. It is 3 by 5 EF. So it is better if you can just remember this. So average energy, or it is written somewhere like this, or it is E over N. This is given as 3 by 5 times the Fermi energy, and the pressure, it is 2 by 3 E by V. Now it has given, in this question you see it is given the Fermi energy EF is equal to 5.51 electron volt, and it is asking the average energy at 0 Kelvin. So when it says 0 Kelvin, we are free to use the form of the Fermi function, where it was a step function. Okay, and when this happens, the infinite integrals, it turns into E to EF, and all the derivation follows. Okay, so this was nothing but 3 by 5 EF. So EF is given, so 3 by 5 into 5.51 electron volt. This is nothing but 3 into 1.102 electron volt. It is 3.306 electron volt. So it is around 3.3 electron volt. This is your answer. Yes. Now the next question is about the Hall experiment. Here what it is saying, in a Hall effect experiment in a metal, a potential of 9 microvolt. So this is your Hall voltage is 9 microvolt, means 10 to the power minus 6 volt. It is developed across a foil of thickness. So the thickness is given. So let us say that this is our sheet and it is a thin sheet, okay, and the thickness T, it is given as 0.04 millimeter, which is 0.04 into 10 to the power minus 3 meter, okay, and a current flowing through this is 1.5 ampere, and there is a magnetic field V is of 2 Tesla, and it is asking what is the Hall coefficient. So the Hall coefficient, it is given as, so this is the definition of, so VH is this. The Hall coefficient is defined as what is the Hall voltage developed divided by the current density times the magnetic field. So that is one of the definition. So why this definition is useful? Because all these quantities can be experimentally measured. From Drude theory, what we got, so it is from the previous derivations that we are doing in terms of number density and all, by balancing the Lorentz force with the force due to Hall effect. So EH and E, and we are putting velocity equal to J over NA. So all these things, this comes from EH equal to VH over T. So this comes from the free electron theory, but the Hall coefficient, if you want to measure experimentally, then you have to find the electric field, or this can be the Hall voltage can be experimentally measured, and this distance D also can be experimentally measured. So B by D, the current density can be measured, and the magnetic field is what you are applying, that also can be measured. So this is a definition of the Hall coefficient. So let us see what we get. So we just have to evaluate this. So VH is given as 9 microvolt. D is what we don't know, it is not given. J is the current density is given I over A, I by A. A is the cross section area, which is this cross section area, and this cross section area is given by this thickness T times this D. So A is given, the cross section area is given by D times T. So D into the thickness T, and so this is your current density and the magnetic field. You see that this cancels this, and we have the Hall voltage times the thickness T into current, the magnetic field. So the Hall coefficient is 9 into 10 to the power minus 6 volt, and the thickness is 0.04 into 10 to the power minus 3 meter divided by the current is 1.5 ampere, and magnetic field is 2 Tesla. We just solve this, so it is 3 and 0.12 into 10 to the power minus 9. So it is 1.2 into 10 to the power minus 10 meter cube per coulomb. So it is just RH equal to 1.2 into 10 to the power minus 10. So this is your correct answer. Now the next question, it is talking about let us see. A patient with a pacemaker is mistakenly being scanned for an MRI. So usually an MRI machine is so uh, there will be a bed and an MRI machine will be here, and this bed slides into this MRI machine, and in this MRI machine, so MRI is nothing, is magnetic resonance imaging, magnetic resonance imaging. So the point is, it will have a very strong magnetic field, and uh, this so there is a person here, and it has a pacemaker, some pacemaker here in his heart. So what is what the question is asking? So there is a 10 centimeter long section of the pacemaker wire, and it moves at a speed 10 centimeter per second perpendicular to MRI units magnetic field. Okay. So let us zoom this particular situation. So this is the 10 centimeter long cross section. So this is 10 centimeter long, that pacemaker wire, and the magnetic field, let us say it is going into the page. The magnetic field, so this is what we have to find, and this is moving. So since this bed is moving into this MRI unit, it is moving at a velocity of 10 centimeter per second, or 0.1 meter per second. Okay, and since it is moving into the this magnetic field, uh, which a certain strength, some B, okay, some there is a, so what is happening due to this is, there is a Hall voltage which is getting induced, and it has a magnitude of 20 millivolt. So since it is moving along this direction, so the Hall voltage will be induced. Let's say, imagine the charge, the electrons here in this is a metal wire. So the electrons are moving in this direction, and the magnetic field is into the page. So the Lorentz force due to this electron will be in the direction of so you have to use F is equal to minus E V cross B. So V is this direction and B is into the page. So if you if you calculate this thing, the electrons will experience a force in this direction, Fl. Okay. So at the end, what will happen is, because of the force along this direction, you will have this side negatively charged and this side positively charged. Okay, and the force Fl on these electrons is F is equal to E V B. E into V cross B, since it is perpendicular to each other, so it will be just V cross B. Okay, and this is what it is talking about. Here, if you know, because of this charge separation, there will be an electric field, and that electric field will be EH from here to here, and because of this Hall field and this distance D, so VH, some potential difference will be developed, and that potential difference will be related to the Hall field as VH over T. Okay. So this voltage, so this will be equal to E times EH. So when the equilibrium will develop, so this has to be balanced by this Hall force. So the this cancels this, so it is V times B is equal to EH, and EH is given by VH over T. Okay, this V is the velocity, and this V is the Hall voltage. This is capital V. We want to find what is the strength of magnetic field. The magnetic field B will be now given by VH over D into velocity. So V is given by VH is what? VH is given by the hall voltage is given as, this is VH, 20 millivolt. So 20 into 10 to the power minus 3 volt, and D is 10 centimeter long, so 10 into 10 to the power minus 2, and sorry, D is 10 centimeter long, and the velocity is 10 centimeter per second. So 10 into 10 to the power minus 2 meter per second. So the magnetic field strength will be, so it is just everything cancels out, and it will be just 2 Tesla. So this is the strength of magnetic field is 2 Tesla. Now we go to the next question. Which of the following is the correct dimensional formula of the 3-dimensional wave function psi of an electron? So psi of an electron is given by 1 over root V e to the power I k dot r. Okay. So this is the formula for the wave function of the electron. So this is just a number, so it has no units, and it is the volume is nothing but L cube. So the dimensionality of this wave function will be 1 over L cube to the power 1 by 2. So it is nothing but L to the power minus 3 by 2, and all other, so L to the power minus 3 by 2, and so M to the power 0 and T to the power 0. So this is your answer. So the next question, it has given the Fermi energy of zinc, EF of zinc, it is given as 9.4 electron volt, and for an unknown metal it is, let's say some unknown metal is EF unknown, it is given as 2.35 electron volt. Okay, now EF, it is given as h bar square over 2m into 3 pi square n, where this n is the number density of the electrons, 2 by 3. Okay, so if you want to find the number density n, how do you find it? So 2m e f over h bar square, or if you want to find, so the easiest way to find EF zinc by so EF zinc by EF unknown, this will be equal to, now see this goes as n to the power 2 by 3, and all other things are constant, so it will be just n number density of zinc to the power 2 by 3 divided by number density of this unknown material, unknown, to the power 2 by 3. Okay, so the number density, so it is asking us to find what is the ratio of density of electrons in zinc. So it is asking us to find density of electrons in zinc divided by the unknown material. You just have to take the power 3 by 2. So EF zinc by EF unknown to the power 3 by 2. So you just put the values. So it is 9.4, 2.35 to the power 3 by 2, and this is 4 to the power 3 by 2, so it is nothing but 8. So the ratio is 8 is to 1. So these are some of the questions of the second assignment of the previous question. Now let us discuss of the previous year some questions of week 3. So it has given you, consider the following form of the wave function, and b is some constant, and it has asked you to find what is the probability of finding the particle in region x equal to -1 to the 1. So this is a basic concept of quantum mechanics, that uh, if psi x is the wave function of the particle, psi x mod square is the probability density of finding the electron. So what it means is psi of x dx is the probability of finding electron, in the interval x to x plus dx. Okay, so what that means is, so the first thing that that one should do when we get the wave function is that we have to normalize it. So normalization is nothing but it is a statement that the particle uh, is existing. So what it means, that if we integrate from -infinity to infinity dx, so this is the probability of finding the particle in the line interval from -infinity to infinity, which is like we are sure to find that the particle is there. So that is why we put it 1. So now we just put this expression. So it will be b square over x square plus 1 dx, integral -infinity to infinity. This should be equal to 1. Now b square is a constant, and dx x square plus 1 -infinity to infinity, this has to be 1. This implies that b square, so dx over x square plus 1, it is the integral of this is tan inverse x from -infinity to infinity. This is equal to 1. So b square, so it is tan inverse infinity minus tan inverse minus infinity. Okay, this should be equal to 1. So tan inverse infinity, so if you see the function of tan inverse x, this is tan inverse x, so it is somewhat like this, and this is approaching to pi by 2, and this is minus pi by 2. So we just put b square pi by 2 minus, so tan inverse of -infinity is minus pi by 2, so minus pi by 2 is equal to 1. This implies b square into pi is equal to 1. This implies b square equal to 1 by pi. So now we got the normalized wave function, b is equal to 1 over root pi. Psi of x is equal to b plus x square root under, and b square we got 1 by pi, which implies b is equal to plus minus 1 by root pi. Okay, so this plus or minus doesn't matter, it will just add to an overall phase, but what we are the only the physically relevant quantity is psi mod square. Now we want to find, the question asks, what is the probability of finding the electron, probability of finding the particle in the interval range -1 to 1. So psi of x mod square dx, this is the probability of finding the electron from x to x plus dx. So now we have to take that limit x equal to -1 to x equal to +1. That will give us the relevant probability. Now psi mod square will be given by, this is b square over 1 plus x square integral dx from -1 to 1. So b square is nothing but 1 over pi. 1 over pi, it is a constant, so we are taking it out of the integral, -1 to 1 dx over 1 plus x square. So just the value of this integral is 1 over pi tan inverse x, x equal to -1 to x equal to +1. So it is 1 over pi tan inverse 1 minus tan inverse -1. So we all know that tan inverse 1 is pi by 4. This is pi by 4 because tan pi by 4 is equal to 1. So pi by 4 is tan inverse 1, and tan inverse -1 is minus pi by 4. So it is, so pi will cancel pi and we'll get 1 by 2. So the probability of finding the particle in this interval -1 to 1 is half. Now we are asked, when we impose boundary conditions on an electron confined in a finite well, so it is about, let us say that confined in a finite well, okay, and only discrete values of k are permitted, okay. When you impose the periodic boundary condition on a string of n atoms of lattice A, how many discrete values of k are there, and what is their spacing? Okay, so what it is saying, there are n atoms of lattice constant A. So this is, so n atoms are there, okay, and with a lattice spacing of A, and it is asking how many discrete values of k are there, okay. So the k is given by, we impose a boundary condition on the electron. So so let us apply first, let us put, so the total length will be n times A, L is equal to n times A. So there will be lot of atom with a spacing of A. So we want to apply the periodic boundary condition. So e to the power, so what we do is the wave function will be given by e to the power I k x. So psi is given as 1 by root v psi kx, okay, and let us employ the periodic boundary condition. The periodic boundary condition, so x plus L is, so we are imposing periodic boundary condition because that is what it is asked in the question, psi of x. So now what we have is e to the power I x I k, so psi of e to the power I k x plus L should be same as e to the power I k x. It is e to the power I k l is equal to 1. 1 is nothing but e to the power I 2 n pi. So n is some integer, n equal to 0, 1, 2, 3 and so on. So basically kl is equal to 2 n pi, since k is equal to 2 n pi over l. L is what? L is Na. So 2 n pi divided by Na. Okay. Now you see what is the spacing of this. So let us write this k. K for n equal to 1. N equal to 0 it is 0. So n equal to 1 it is 2 pi by Na. 2 pi by capital N A. So what we are doing is we got k equal to 2 n pi over Na. So along this axis we are writing what are the allowed values of k. So 2 pi over Na. Then we put n equal to, this is for n equal to 1. If we put n equal to 2, it will be 4 pi over Na. And it will be then 6 pi over Na. So the spacing between this is, you see, the spacing between this is given by 2 pi over Na. Okay. So the spacing we got as 2 pi by Na. So now we want to see how many discrete values of k are there. So since the smallest spacing can be a, so we want to see what is there in this how many states are there in one Brillouin zone. So one Brillouin zone will be given by 2 pi by the length of the length occupied by one atom. 2 pi by the length occupied by one atom is what? If you just see this placing of this arrangement, you see that periodicity is A. Since the periodicity is A, every spacing of A will have one atom. Okay, so we'll just, so length of Brillouin zone will be 2 pi over A. So in this 2 pi over A, there are so this is the length of one Brillouin zone. Now length of one Brillouin is 2 pi by A, and spacing between the k values, we saw that it is 2 pi by L, and L is Na, so 2 pi over Na. Now we look at the k axis. In the k axis, let us say this is 0, and one Brillouin zone is given by it is of length 2 pi by A. So this 2 pi by A we can just write as pi by A 2 minus pi by A. So this distance is 2 pi by A. Okay, and here there are a lot of the k values, and these k values, each of these are separated by 2 pi over L. This is the spacing. So the number of distinct values will be given by, so these are very small spacings which is separated by 2 pi by. So the number of distinct k values will be given by this distance 2 pi by A divided by this spacing. So 2 pi by A divided by the spacing. The spacing is how much? 2 pi by L. So if you just simplify this, it will be L by A, and L is nothing but Na divided by A. So it is N. So what we have is uh, so therefore we got that there are n discrete values which are spaced at this interval 2 pi over n. Now we go to the next question. Consider two hydrogen atoms with their electrons at ground state energy epsilon naught. When the two atoms are brought close together, the electrons start hopping with energy T, and we want to find what is the ground state energy after allowing for hopping. So let us say that we first consider, before the hopping is allowed, this is hydrogen atom H and this is hydrogen atom H, and we are uh, let us say that there is only one energy level epsilon naught, and here the electron is in energy level epsilon naught. Since they are far away, so the total energy will be how much? Now the total energy is the electron of this hydrogen atom is at epsilon naught initial total energy epsilon naught plus the energy of the electron of this hydrogen atom is epsilon naught. It is 2 epsilon naught. Now when they are brought close together, then uh, this is then we are allowing a hopping, and we want to find the change of the ground state energy. So for this we can just use the variational principle. uh, so when the two hydrogen atoms are close together, are very nearby to each other, so this is the nucleus, this is nucleus, so the Hamiltonian H will be given by, let us say that the, so here the Hamiltonian was earlier the kinetic energy of the electron plus the potential energy due to the nucleus, the first nucleus. Okay, let us say that the eigenstate was 1 and the energy, eigenvalue energy was epsilon naught, and here H is equal to T plus V2. V2 is the energy of, V2 is the potential energy due to the nucleus 2 on the electron, and here let us say that the state is denoted by this ket2, and the eigenvalue energy as epsilon naught. But now since they are close together, when they are close, then what we have is T plus V1 plus V2. Okay, and let us assume so we want to do some variational calculation. So psi is equal to, we can just write some value u1 times 1 plus u2 times 2. Okay, now what we want to do is, we basically want to find, after allowing the hopping term, what is the ground state energy. To find that ground state energy, we want to find, so E variational psi H psi over psi into psi. If you assume for the orthogonality of 1 and 2, then what we will get is u1 square plus u2 square. You can just evaluate this integral, and epsilon naught minus 2t u1 u2, where t is what? T is equal to 1 v1 2 is equal to so minus of t, and or 2 v2 and 1, and denominator is u1 square plus u2 square, or this can be written as, so E variational I can just write E u1 square plus u2 square into E will be equal to u1 square plus u2 square epsilon naught minus 2t u1 u2. So what I want to do is I want to minimize this. So we have to take the derivative with respect to u1 and u2. If you do the derivative with respect to u1, then the equation you will get is u1 is equal to u1 epsilon naught minus t minus t u2, and u2 is equal to u2 minus t u1. So this system of equations, this can be written as a matrix form. So E u1 equal to u1 minus t u2, and E u2 equal to minus t u1 plus epsilon naught u2. So this can be written as E times u1 u2 is equal. Epsilon naught minus t u1 u2. So this energy, it can be found by just finding that this determinant minus t or so this can be written as slot minus E minus t u1 u2 is equal to 0. So this equation can have solutions if this determinant is 0, minus 2 epsilon naught minus E, this determinant has to be 0. So it is epsilon naught minus A whole square minus t square is equal to 0. So what we have now is epsilon naught E is equal to epsilon naught minus E whole square is equal to t square. So if we take the square root, epsilon naught E is equal to epsilon naught plus or minus t. So now there are two energy levels. So earlier the energy levels was epsilon naught, but when they are brought close together, we get one energy level epsilon naught plus t and epsilon naught minus t. So this is what we got, and we want to find the change in energy. So the change in energy will be given by so let us now just do that. Epsilon naught when they are far away, and when they are brought close together, it is epsilon naught plus t, and it is epsilon naught minus t. So earlier both the electrons were in epsilon naught. So initial total energy is equal to 2 epsilon naught, one for this electron and one energy for this electron. Now the final total energy will be so epsilon naught minus t for one electron, and for the other electron also will be epsilon naught minus t. So it is 2 times epsilon naught minus t. So change in energy will be 2 epsilon naught minus t minus 2 epsilon naught is equal to minus 2t. So this is your answer. in this question it is asking uh, the translation operator tx, it has given t of a acting on x will change the state to x plus a, and t of 0 is nothing but the unit operator. So we have to choose which of this is correct. So let us verify this. So the LHS is, so to whenever we want to see the equivalence of the operator, then what we have to do is we have to operate the operator on a state. So the left hand side is Ta times Tb. Let us operate that on a state. So this is some arbitrary state. So this can be, so now what this means is Ta operating on the state given by the state obtained when Tb operates on x. So when Tb operates on x, by this definition what we will get? So x plus b. Now Ta when operates on x plus b, so again we will apply this definition. So it is x plus b plus a. Okay, now b plus a, it is same as x plus a plus b, this state, and this state can be obtained by operating t in of a plus b operating on x. Okay, so the effect of t a plus b operating on x, which is giving this, is same as t a and t b operating on x. So that is why these two operators are the same. So this statement is correct. Now let us see this, the second part, if it is correct or not. So T A inverse of x, is it same as, it is asking, is it same as T of A operating on x? Now T of A operating on x will give you x plus a. Okay, so what the inverse operator means? So inverse of operator means T of A into T of A inverse of x should give me, so since it is the Ta is the inverse of Ta, it should give me back x. Okay, or Ta inverse of T of A x, it should give me x. So the inverse of an operator means it is the identity operator. Okay, so let us see if it is identity operator or not. So T of A inverse Ta of x is x plus a is equal to x. So the action of T of A inverse has to be, so this has to be x plus a. If the action of this on this has to be minus of a, then only this can be satisfied. Okay, so what we have to do is T of A inverse has to be T of minus a, then only it is satisfied. Since it is not doing it, so this statement is wrong. Now let us see if this is so let us talk about this statement. So it is saying T of A, so once we have done this calculation, we know that this statement is correct, statement D is correct. So let us now verify statement C. So it is saying T of A T of B is same as T of B T of A. So if it is operating on x, are we getting the same state or not? So this we want to verify. So this will give me T of A x plus b, and T of A acting on this will be x plus b plus a. Okay, and this gives me T of B, T of A plus x, it will give me x plus a, and T of B of x plus a, it gives me x plus a plus b. So these two states are same. Since the two states are same, these two operators are the same. So the correct answers are A, C and D. So another easy way, like an operator of this type, it in the position space it is written as e to the power I k x. So t of x, or like if you want to find t of a in the position space, it is e to the power I k a. So now you just e to the power I k, you can put all this formula here and check if it is correct or not. So for example, if you want to verify this, e to the power I k a into e to the power I k b is equal to e to the power I k a plus b. So you can verify similarly all other things and you will get this formula. So t of a has the form e to the power I k a. Now we have this question. Sodium has a volume expansion coefficient. Sodium has a volume expansion coefficient beta is given, which is 15 into 10 to the power minus 5 per Kelvin. So what is beta? It is just 1 by volume dou V over temperature at constant pressure. So it is beta. So it is asking what is the change in the Fermi level as the temperature is raised from 0 to 300 Kelvin. So the Fermi temperature EF, it is actually a function of, so h bar square over 2m 3 pi square n v to, 2 by 3 over v to the power 2 by 3. See, if the temperature is raised from 0 to 300, then what can be affected is the volume can be changed, because like sodium has some thermal coefficient of expansion. Because of this change in the volume, the number density will decrease and hence the Fermi energy will decrease. So it is asking how much is that change of that Fermi energy. So the way we approach this is, we want to find the change in the Fermi energy, and this is a function of, so this change, so we have to first write EF is a function of some temperature and volume. So this will be dou E by dou T EF dt plus dou EF by dou V dV. So now we see we want to find what is this as a function of temperature. So dEF by dt, so the change of this with respect to temperature, it is given by dou EF by dou T plus dou EF by dou V dV by dt. Okay. Now see, EF has no explicit dependence on temperature, so this quantity goes away. Okay, and EF, since it depends on this volume, EF is it is dependent on this volume as e to the power V to the power minus 2 by 3. So dou EF by dou V we can calculate. So it is h bar square over 2m 3 pi square n to the power 2 by 3, and it is minus 2 by 3 into V 2 by 3 and 1 by V. So if you just do this derivative, you see that this quantity is again same as EF, so it is minus 2 by 3 EF by V. Okay, so that is the value of the derivative. So what we have is dEF by dt is same as So here we put this value minus 2 by 3 EF over V and dV by dt. Okay, so now what we can do is dEF by dt is equal to minus 2 by 3 EF 1 by V dV by dt. Now see, 1 by V dV by dt is nothing but your beta. So 2 by 3 EF into beta. Okay, and it is asking, so the question was to find what is the, so EF I can take it this side, I can rearrange this as minus 2 by 3 beta into dt. Okay, so and this has been given as 3%. 3% means is it 3%? So this is what we have to find, what it is. This is what we have to find, what is the percentage. Beta has been given, dt is given, dt is change of temperature from 0 to 300. So minus 2 by 3, beta it is given as, what is beta? Beta is 15 into 10 to the power minus 5. 15 into 10 to the power minus 5 per Kelvin. Dt is 300 minus 0. Okay, so dEF by EF, it is nothing but, so 3 will cancel 5, so it is minus 10 into 10 to the power minus 5 into 3 into 10 to the power 10 to the power 2. So 3 minus 5, it is 3 by 100. So, and this negative implies that there will be a decrease of the Fermi energy. So decrease of the Fermi energy by 3%. So this is your answer. Now it is asking, consider a three-dimensional simple cubic lattice with number of unit cells n. So n is the number of unit cells and the number of allowed k values is so the number of k values is the same as the number of unit cells in the crystal. So that is why it has to be equal to n. So it is just the same technique that we had. So it is just the generalization of the same technique that we did for the one-dimensional Brillouin. So it is the number of distinct. So we just saw before that in a Brillouin, the number of distinct k states. It was number of distinct k states was n, and in the real space also we had with a lattice spacing of A, there were n of these atoms. Okay, so by the similar logic, the number of allowed states, so that this logic can be generalized to the 3 dimension, and the number of k values is n. So that is the those are the questions which I wanted to discuss with you. If you have any other questions or doubt, you can ask me. You have any doubt or query? If not, then we can end the meeting here. Thank you.